Hi and welcome back to this channel. So in this video we'll be talking about the next strategy for our scheduling problem. If you can remember from the last video, we talked about the first come first serve strategy, we talked about the smallest degree first, and we also talked about the shortest jobs first. So in this video we'll be looking at the fourth strategy, and that will be the earliest finish time strategy. The earliest finish time strategy. And in this strategy we want to execute jobs with the earliest finish time first. For example, if we have this job, this job, let's just list some jobs. So we want to check for this job finishes first, so we pick it. What jobs finishes right after this one finishes and doesn't overlap with this one? We can't choose this one because it overlaps with this. So the next job would be this one, and the next job will be this one because it doesn't overlap with this and it has the next finish time. When we choose this, we won't choose this one on top. We won't choose this because it overlaps with the third job, right? And after that, we'll choose this job because it has the earliest finish time. So altogether, we execute 4 jobs using this method. Will this method work all the time? That's the question we want to ask. Why? If you say yes, why would it work all the time? If you say no, why won't it work all the time? So I think this method will work all the time, and because it has the least number of conflicts. It has a maximum number of disjoint intervals which finish first. So because we are choosing jobs that finish first, we're also maximizing our time such that the time it requires to do the most number of jobs will be smaller than in the other strategies. And we cannot have 2 intervals finish before the interval we've picked. For example, since we've picked this one, no other job finishes before it, right? If we pick this one, no other job finishes before it, so no other eligible job. I think we should use the word eligible because this finishes before this one, but it's not eligible because there is an overlap. So no other eligible job finishes before it. So having said that, let's look at our proof. How do we prove that this is the best method? Before we go into the proof, I'm sure you must have heard, or you might know 1 or 2 things about greedy algorithms. Greedy algorithms are algorithms that make the best decision based on where it is at the moment or based on the current time. A greedy algorithm will make the next best decision based on the current time. And this earliest finish time strategy is a greedy algorithm, and that's because at each point where it makes a decision, it makes the next best decision. It makes its decision at each point, at each time. After every job finishes, it makes the next decision. Unlike first come first serve, which is just a rule. It's more of just a rule. It does not make decision at every point. Considering the shortest job first and the smallest degree first, which do not make decisions at the end of every job. Our earliest finish time makes a decision at the end of every job, and that is what makes it a greedy algorithm. It makes decisions at the end of every job. So when each job finishes, it chooses the next best job to execute. So we are going to move on to writing our proof. We'll call this proof of correctness. by induction. I'm sure we all know one or two things about induction, where we start with the base case and then we generalize, right? So we have our proof of induction, no, our proof of correctness by induction. That's what we call it, proof of correctness by induction. And our aim for this proof, what we really want to show in this proof, is that our greedy algorithm performs better than any other optimal algorithm. Our greedy algorithm, we want to prove that the greedy algorithm always performs better than any other optimal algorithm. So we want to prove that greedy performs better, or let's say stays ahead or performs better than any other solution. That's everything we want to see in this proof. And to start this proof, we're going to define what our greedy algorithm is, what the other optimal algorithm is, and a measure of goodness. Measure of goodness would be any measure at all that shows that our greedy is staying ahead. So let's start up with this proof. Let's start up with our definitions. Let's call this AI, and AI would be the first I intervals with our greedy algorithms, the first I intervals or jobs. In this case we're talking about jobs. So AI is the first I intervals or first I jobs chosen by greedy. And come to think about it, if we are saying that greedy performs better or stays ahead than any other algorithm, what we are trying to show is that using the same time, greedy would perform more jobs using it in a given time, using a particular given time. Greedy would perform more jobs than any other algorithm. So let's call any other algorithm or solution OPT I. So this would be the first I interval chosen by the optimal solution. The same thing we have here, but chosen by the optimal solution. And our measure of goodness. So how can we measure how good our greedy is? That's what our measure of goodness is. Let's call that M of S. How do we measure goodness in this scenario? For this scenario, we can say that the finish time of the last interval by our greedy is shorter, right? If the finish time of the last job done by greedy is shorter than the other jobs, it means our greedy is doing better. So we can say that for our measure of goodness, the finish time, we can measure our goodness with the finish time of the last interval. This will be a measure of goodness. You can as well define your measure of goodness in other terms, but for this scenario, I decided that using our finish time as a measure would be appropriate for measuring greedy against any other algorithm. So moving ahead, after our definitions, like I said, when writing your proof of correctness by induction, you start by defining your greedy, your optimal, and then your measure of goodness. The next thing we want to do right now is to make our claim. And our claim, the next thing you do after definitions is your claim. And like I said before, our claim is that greedy is better. Greedy stays ahead, right? And using our measure of goodness, which is the finish time of the last interval, if greedy is better, it means greedy is finishing earlier. So to write that, we say M of the greedy, which is AI, is less than or equal to M of the optimal solution for all jobs, for all I, where I is the job, right? So what this is saying in essence is that greedy finishes earlier. When we use the greedy strategy or the greedy algorithm, we finish earlier than when we use any other algorithm. This is based, I'm going to say again that this is based on our measure of goodness. Since our measure of goodness is the finish time, we are using the finish time as a yardstick for measuring the goodness of a greedy algorithm and any other optimal solution. This is the case. If you redefine your measure of goodness, this expression might not necessarily capture, using less than or equal to might not necessarily capture that your greedy algorithm is doing better. So this depends on what your measure of goodness is. So moving on, we've made our claim, and let's use an illustration to show what we mean, what this claim means. This claim means that for this, using the optimal algorithm, this is the ith job, right? 1, 2, 3 to the ith job. But when you use the greedy, let's call this greedy. When you use the greedy, you have this, you see that for each interval, when you compare the greedy and the OPT, the greedy is finishing faster. And by the time you get to the ith, the greedy also finishes faster. So you have, this is the MEI and this is the MOPTI. This is just, an illustration of our claim. So now let's actually get into the main proof. Let's start with our base case. Our base case is when our job, we just have one job, I is 1, when we have only one job. And when we have only one job, whatever optimal strategy would do just that one job, and our greedy would do just one job. So this, I think, using our base case where we have this is one job, this is one job, whether you use the optimal or the greedy strategy, it makes no difference because it's just one job. So our claim is still correct. So our claim, this claim we have here, is still correct. So let's move on to the induction. By induction, let's assume that we want to assume that, let's write, assume that the greedy for, this is 1, for the job before the last job is still less than this, right? So if, let's use an illustration. If we have this one, so just as we did before, and we have I minus 1, then I, it means that when we use a greedy, we would also have, the greedy algorithm should give us something like this, I minus 1, and this, right? So from this, we also see that the greedy does better than the OPT with respect to time, and our claim still holds. So this is just a rough sketch of what the proof of correctness by induction for this strategy. This is just what it looks like. From our next video, we are going to be giving more examples of greedy algorithms and writing proofs for them. And we'll stop here for now. If you liked this video, do well to comment, share, and I'll see you on the next one.